we're going to look at a nice extension of what might be the internet's favorite math formula. That's Euler's formula for the complex exponential. And in particular, today we're going to look at what I'll call a quaternionic version of e to the I theta equals cosine theta plus I sine theta. This is, again, Euler's famous formula. And let's first recall what the quaternion algebra is, which can be thought of as some sort of generalization of the complex numbers. So it's generally denoted by H for Hamilton, as Hamilton was the person that found the quaternions. And that's a linear combination of these vectors I, j, k, along with the real number 1. So in other words, it's everything of the form a plus bi plus cj plus dk, where a, b, c, and d are real numbers. And then we've got a multiplication rule for I, j, and k that goes like this. They each square to -1. So we have I squared is the same as j squared is the same thing as k squared, which is -1. And then I times j is k times j is I, and k times I is j. But then if you reverse the order of those multiplications, you pick up a minus sign. So j times I is -k times j is -I, and I times k is -j. And you can remember that with this nice little loop here. So if you follow this loop in the direction of the arrows, you just pick up a plus sign. But if you follow it in the opposite direction, you pick up a minus sign. So I times j is k, whereas j times I is -k because we went against the arrows. So before we get started on our main goal, let's look at a couple of example calculations. Let's multiply these two quaternions. We have 2 plus 3i plus 4j times I minus 2j plus k. So let's see, we've got to multiply out several things here. So we need to do 2 times I, that'll be 2i, 2 times -2j, that'll be minus 4j, 2 times k, that'll be 2k. So that's everything with this first term sorted. Now let's do the second term. So 3i times I will be -3. That's because I squares to -1. 3 times -2j will be 6k, and it'll be -6k. So minus 6k. So let's talk our way through that. That's because 2 times 3 is 6, and then I times j is k, like over here, so that means we maintain this minus sign. Okay, so now 3i times k will be -3j, based off this rule right here. Now we're into the 4j part, so 4j times I will be, let's see, -4k, because we're multiplying in the opposite order. 4j times -2j will be +8 because j squared's to -1, and then 4j times k will be plus 4 times I. Okay, great. So now we just need to combine like terms. So let's see what we have for our constant terms. I really shouldn't say our constant terms, our real part. So we have a -3 plus 8, so that will be 5. And then what do we have for my I component? So everything with an I, j, or k is considered an imaginary part. So the imaginary part here is 3-dimensional. So we have 2i and a 4i, so that will be plus 6 times I. And then what do we have for j's? So let's see. We have a 4j here and a 6 and a 3j over there, but they're both negative, so that's minus 7j. And then what do we have for k? Let's see, we have 2k minus 6k, that's -4k, minus another 4k, so that's going to be minus 8k. So that would be the final version of our product. Okay, so I think that's good for our example calculations. One thing that I would like to leave you with before we move on to our main result is maybe a little bit of an exercise for you to try on your own. And this exercise gives you some sort of idea for finding the inverse, the multiplicative inverse of a quaternionic number. So let's show that a plus bi plus cj plus dk dk inverse is equal to a minus bi minus cj minus dk over a squared plus b squared plus c squared plus d squared. So that's kind of like in parallel with what happens with complex numbers. You have the conjugate over the modulus squared, and that's exactly what's happening here. So how would you check something like this? Well, you would check that this object right here multiplying into this object right here indeed gives you the number 1. So like I said, I'll let you check that. That's not so hard to check. Okay, so now that we've kind of warmed up with our arithmetic of quaternions, let's move into our main result. So let's move on to our main result, but before we do so, let's write a somewhat more general version of this complex exponential formula. And we'll do that for, instead of e to just an imaginary number, we'll do it to a non-imaginary complex number. So maybe we'll write it like this. So let's recall that if z is equal to a plus b times I, which is a complex number, then e to the z, well, that's e to the a plus bi, but that's going to be equal to e to the a times e to the bi, using, exponential rules. But then we can expand this out using our formula over here. This is e to the a, and then we'll have cosine of b plus I times sine of b. Okay, so now this is really the formula that we want to generalize, this thing that's slightly more general, I guess, than this simple thing right here, this Euler's formula. And let's focus on this extreme left-hand side and right-hand side, and we should be aiming to something of that form. Okay, so let's introduce some notation. So instead of using a letter Z or a letter W, which is generally reserved for complex numbers, let's use a letter Q. So let's let Q be A plus BI plus CJ plus DK, and we're thinking about this as a quaternion. And now let's introduce a little bit more notation. So let's set b equal to the square root of b squared plus c squared plus d squared. And then we'll set capital I equal to b times I plus c times j plus d times k over b. Okay, so you can think of I as being some sort of scaled version of the imaginary part of Q. Notice it's exactly the imaginary part of Q divided by B. And in fact, under this rewriting, we have Q is equal to A plus capital B times capital I. And this is meaningful because now it looks a little bit like a complex number. We're using uppercase letters instead of lowercase letters, but what we will show is that this indeed behaves a lot like a complex number. And in order to see that, we'll first notice that capital B is a real number just based on its construction, and then I squares to -1. So let's do that. So let's square I. So that's going to give us what? It'll give us BI plus CJ plus DK squared, but I'll just write them next to each other so we can easily multiply everything else, over b squared, but b squared will be this object right here. So we have b squared plus c squared plus d squared. Notice I just took it out of the radical. Okay, so now let's multiply out that numerator there. And let's multiply the like terms first, just to keep it simple. So we have bi times bi, so that'll be negative b squared, because I squared is to -1, lowercase I. Then cj times cj will in turn be minus c squared, and then dk times dk will be negative d squared. And then let's see what else we have. We have plus b times c, and then that's going to be attached to I times j plus j times I. So it's I times j from this product right here, and it's j times I from this product right here. Notice the real parts of these, or these real coefficients, commute with everything, so that's why we're able to pull it out like this. And then let's also look at b times d and its coefficient. So that coefficient will be I times k and then k times I. So we have ik plus ki. And then finally for CD, we'll have j times k plus k times j. And then this is all over b squared, capital B squared, which again was b squared plus c squared plus d squared. And now lots of you are probably screaming at me to cancel some things out, and that's what we'll do right now. So we're going to use the fact that I times j is k, but j times I is negative k. So that means if you add these two together, you'll get the number 0. Likewise, if you add these two together, you'll get 0, and these two together, you will also get 0. So now putting this all together, we've got negative this sum of squares over the sum of squares, which means we have negative 1. Okay, so that means up here I'm going to add the little result that capital I squared is equal to negative 1, and then we'll go from there. So on the last board, we took a general quaternion and we wrote it in the following form. So we have its real part and then its imaginary part. And the important part is we rewrote this imaginary part so that this capital I squares to negative 1. So this behaves like a complex number. So it behaves like a complex number when you exponentiate it. So it doesn't behave like a complex number if you combine it with totally different quaternions, because they'll have different versions of this capital I. But when it comes to combining it with itself, it really behaves exactly like a complex number. And so since it behaves like a complex number, we can exponentiate it using the complex exponential formula like this right here, or the more general version like this right here. So let's do that. So now we'll have e to the q will be the same thing as e to the a plus capital B times capital I, but that's going to be e to the a times e to the capital BI. But again, since this capital I is like an imaginary unit, when it interacts with itself, we can apply this formula up here that's underlined in blue. So that's going to give us e to the a, and then we'll have cosine of b plus I times the sine of b. But now we can rewrite this formula using maybe what b and capital I are, and then we have our quaternionic version of this famous formula. So let's see, we'll have e to the q will be e to the a, and then it will be the cosine of the square root of b squared plus c squared plus d squared, and then plus bi plus cj plus dk over that square root, so b squared plus c squared plus d squared, and then the sine of that square root, b squared plus c squared plus d squared. And then, even though this is quite wordy, this is in fact the quaternionic version of this formula. Okay, so now I'd like to play around with this formula a little bit to see if we can get some interesting results. So on the last board, we derived the following quaternionic version of our famous formula from Euler. Now we're going to look at a couple of applications of this formula. So let's notice that e to the I times pi over 2, where this is the quaternionic number I, not the complex number I. So this will be e to the 0, because here a is equal to 0. And then we'll have cosine of the square root of pi over 2 squared, plus 0 squared plus 0 squared. And then plus, well, we'll have pi over 2 times I over the square root of pi over 2 squared, kind of for the same reason. And then again, the sine of the square root of pi over 2 squared. Okay, so something like that. And of course, like I wrote out way too many details because this simplifies quite a bit. So this is going to give us cosine of pi over 2, which is 0. This coefficient of I will turn into the number 1, just given the quotient we have, and then sine of pi over 2 is the number 1. So this is in fact equal to I. So that means we have I equals e to the I pi over 2. And then very, very similarly, we have j is equal to e to the j times pi over 2, and k is also equal to e to the k times pi over 2. But then these three things together can be used to do a quaternionic version of a really famous YouTube math problem. And so that really famous YouTube math problem is, what is I to the I? So let's recall that I to the I is e to the minus pi over 2, and there are several videos that do this result. But what about, instead of imaginary to imaginary power like that over there, we do quaternion to quaternion power? Well, notice by essentially the same sort of argument that takes us to I to the I equals e to the minus pi over 2, we also have j to the power j is equal to e to the minus pi over 2, and k to the k is also equal to e to the minus pi over 2. So I think that in itself is interesting. So we've got three cases where quaternion to quaternion equals real number, or maybe imaginary quaternion to imaginary quaternion gives you a real number. But those are not actually super interesting, because if we're only working with I on its own, or j on its own, or k on its own, we might as well just be working in the complex numbers, because those are each copies of the complex numbers injected into the quaternions. I think maybe what's interesting is what happens if we do I to the power j. Okay, so let's do this calculation. So if we do I to the j, this will be e to the I pi over 2 raised to the j power. Okay, but now we can use exponent rules to rewrite this as e to the ij times pi over 2. But I times j is equal to k, so this is in fact equal to e to the k times pi over 2, which is equal to k. So I think we've just shown that I to the j is equal to k. But let's maybe like double check this. And we can double check that using a really crazy trick involving the matrix realization of the quaternions. So let's also recall the following complex matrix representation of the quaternions. So a plus bi plus cj plus dk can be, like I said, represented by the matrix a plus bi, a minus bi on the diagonal, where we're thinking about that I as being a complex number, whereas this I is like the quaternionic number. And then here we'll have c plus di, and then minus c plus di on the off diagonal. And then we're also going to use another thing, and this is something that I've done in a very old video that I think I might update, and that is we're going to use this formula for taking a matrix to a matrix power. So let's recall, to take a matrix to a matrix power, well, we rewrite this as the exponential of a certain product of matrices. And that's going to be e to the log a times b, where there we've taken a matrix exponential and a matrix logarithm. And then what you can check using this is that if you take I to the j in this setup, we'll have the matrix I, 0, 0, minus I to the power 0, 1, 1, 0. But then that's going to in turn be equal to the matrix exponential of the logarithm of I, 0, 0, minus I times this matrix right here, 0, 1, negative 1, 0. I think I missed a minus 1 there. But now if you do that calculation, what you'll see is that you get 0, I0, which is exactly the matrix for k. So it seems like we're able to do it this way and we're able to do it this way and get a similar result. So does that mean this is a reasonable way of defining this quaternion to a quaternion exponential? Well, in fact, it's a little bit sketchy. And you can check out this short video that I made to describe why this is a bit of a sketchy calculation. And that's a good place to stop. Thanks for watching and sticking around until the end of the video. And since you're here, don't forget to gently press that like button, subscribe, ring the bell, and select all notifications to never miss a video. If you want to get your name in the credits like you see here, access the live seminar series, review videos before release, and more, go to patreon.com/michaelpennmath and become a Patreon member today. If you want full ad-free course content, subscribe to my second channel, Math Major. I've got courses on linear algebra, complex analysis, and proofwriting, among several others. And that's everything. Bye.